Hey everyone! Tonight we're diving into the salt, stained hands, and systematically destroyed spines of ancient shipbuilders. The maritime craftsmen who built the floating coffins that carried empires across treacherous seas and gave us watertight compartments, ocean-going commerce, and the subtle art of creating vessels that might actually make it to their destination without becoming expensive driftwood. So before we begin this journey into organized nautical suffering, take a moment to like the video and subscribe, but only if you genuinely enjoy watching me explain how humans voluntarily spent their lives transforming trees into seaworthy torture devices. And drop a comment letting me know where you're watching from and what time it is for you right now. It's always fascinating to see who's joining us from around the world, probably in buildings that are infinitely more structurally sound than anything these ancient craftsmen created while freezing in medieval shipyards. Now, dim those lights. Maybe grab something warm to drink, because we're about to spend time in places where workplace safety was a revolutionary concept that wouldn't be invented for another 1,000 years, and let's settle in for tonight's exploration together. So, you think you could handle ancient shipbuilding? Charming. Really? Like someone thinking they could perform brain surgery because they once successfully assembled IKEA furniture without crying. You imagine yourself as a master craftsman, creating elegant vessels through satisfying woodwork and meaningful collaboration with skilled artisans. What you don't imagine is discovering that skilled craftsmanship means your hands become a topographical map of scars. Woodwork involves lifting timbers that weigh more than small houses, and collaboration means working alongside men whose life expectancy was roughly equivalent to their ability to avoid being crushed by falling masts. But sure, let's explore your inevitable maritime awakening, shall we? Before you could even dream of launching vessels that would carry empires across treacherous seas, you had to make it through apprenticeship, the ancient world's version of a survival reality show, except the only prize was a lifetime of splinters, back pain, and the constant fear that your next creation might become someone's very expensive coffin. Step 1. Present yourself to the master shipwright. Hands out, shoulders broad, expectations tragically high. The master shipwright has seen 1,000 eager faces and buried half of them after workplace accidents that would make modern safety inspectors weep into their clipboards. He examines your hands, not to admire your manicure, but to determine if you have enough fingers to be useful and whether they're strong enough to grip tools that were designed by people who believed suffering built character. Weak grip, rejected. Fear of heights, absolutely rejected. Inability to swim, surprisingly, not automatically disqualifying, because most ancient shipbuilders couldn't swim either, which tells you everything you need to know about the logic of this profession. What mattered was whether you looked like you could lift heavy timber without immediately herniaing yourself, whether you could work in conditions that would challenge a mountain goat's sense of balance, and most importantly, whether you had the kind of face that said, "Yes, I'm stupid enough to spend my life building floating death traps." If you made it past inspection, congratulations. You were now considered apprentice material, which in ancient terms meant unlikely to die on the first day, but we're not making any long-term bets. And yes, you had to swear an oath not to any god of craftsmanship or safety, but to your master, who probably hadn't seen his family in months, because he lived at the shipyard like some kind of maritime hermit crab. This oath was binding in ways that would make modern employment contracts look casual. Break your commitment, and you weren't just fired, you were blacklisted from every shipyard within trading distance. Still interested? Excellent. Now grab that adze, ignore the bloodstains from previous apprentices, and prepare for the next decade of learning why ancient civilizations considered shipbuilding only slightly less dangerous than active warfare. They called this a noble profession. Craftsmen lined up for it. Some were even excited. Adventure on the seas, they said. Essential to commerce and empire, they said. Most of them changed their minds after their first encounter with a ship timber that weighed more than a small house and had to be moved using nothing but rope, wooden levers, and prayer to whichever deity handled workplace safety. And don't think being born into a shipbuilding family made it easier. In fact, it made it inevitable. If you were the wrong combination of coastal, dwelling and male, Congratulations, the shipyard was your destiny, your inheritance, and quite possibly your tomb. Of course, if you weren't from a shipbuilding family, you could still learn the trade. They just started you with the most dangerous jobs, paid you in food scraps and optimism, and assumed you'd either prove yourself worthy or provide a cautionary tale for the next batch of hopefuls. But that's just the recruitment process, so you made it past the master's inspection. You're in. Hooray! Now the real education begins, the systematic destruction of your naive assumptions about what building ships actually involves. Forget everything you think you know about construction. You're not building a house that will sit peacefully on solid ground. You're creating a wooden box that needs to float while carrying tons of cargo, survive storms that can crack mountains, and remain watertight despite being made from materials that naturally want to rot, split, and sink. Your new identity was wrapped in wood shavings, tar stains, and the permanent smell of whatever marine adhesive had soaked into your clothes last week. Your hands would become a topographical map of cuts, splinters, and burn marks from hot pitch. Your back would develop the kind of permanent curve that came from years of bending over massive timbers while pretending you weren't slowly destroying your spine. Your work clothes, one size fits nobody, designed by people who believed comfort was the enemy of productivity. Everyone dressed the same, worked the same, bled the same. Want to express individuality? Try carving your initials into a beam and see how quickly the master shipwright explains why personal touches weren't welcome on vessels where lives depended on standardized construction techniques. The shipyard was organized chaos populated by men who traded normal life expectations for the privilege of working with materials that actively tried to kill them. Your new colleagues were specialists in different forms of misery carpenters who could shape timber into impossible curves, caulkers who spent their days stuffing gaps with materials that would hopefully keep the ocean outside where it belonged, and riggers who climbed to heights that would terrify professional acrobats while carrying equipment that weighed more than they did. Individuality wasn't just discouraged, it was dangerous. A creative interpretation of traditional construction methods could result in a ship that looked beautiful in the harbour and disintegrated the first time it encountered serious waves. If you smiled too much while working, the master might assume you weren't taking the life and death nature of your craft seriously enough. Enjoying yourself was suspicious because anyone who truly understood shipbuilding should be appropriately terrified by the responsibility. You worked in teams of 8 to 12 men, depending on the project. If one person made a mistake, everyone suffered the consequences when the ship either sank during sea trials or returned to port in pieces. If someone had a bad day and miscalculated a joint, you all got to explain to the merchant who'd commissioned the vessel why his investment was now decorating the ocean floor. And about your tools, they weren't suggestions. The adze for shaping curved timbers, the broad axe for rough work, the drauk knife for smoothing surfaces, the auger for drilling holes, and the caulking iron for sealing seams. Each tool required years to master and could maim you in creative ways if you used it incorrectly. The adze in particular was basically a sharp blade attached to a handle in a configuration designed to remove as much flesh as possible if your grip slipped even slightly. But let's start with the basics, selecting timber, because before you could build a ship, you needed to find trees that were willing to become floating transportation instead of staying safely rooted in the ground where they belonged. Timber selection was both art and gambling. You needed wood that was strong enough to withstand oceanic violence, flexible enough to bend without breaking, and available in the massive quantities required for anything larger than a fishing boat. Oak was preferred when you could get it dense, durable, and naturally resistant to rot. Cedar was excellent for areas that needed to be lightweight. Pine could work for less critical applications, though it required more maintenance and prayer. But here's what they didn't tell you about ancient timber harvesting. The trees you needed were usually located in places that were specifically designed to make extraction as difficult as possible. The best ship timber grew in forests that were inaccessible by road, located on mountainsides that required pack animals and human determination to navigate. or situated in swamps where the logistics of moving massive logs involved engineering challenges that would stump modern construction crews. You'd spend weeks in forests, living in conditions that made the shipyard seem luxurious by comparison, identifying trees that met specifications that were simultaneously precise and flexible. The timber needed to be straight, grained for structural strength, but certain pieces required specific curves that could only be found in trees that had grown in particular ways. A tree that had been bent by wind might provide the perfect piece for a ship's ribs, while a straight trunk could be shaped into a keel or mast. Felling trees with ancient tools was an exercise in controlled violence that required coordination between multiple people wielding axes that could remove limbs along with branches. Each tree had to be brought down in a specific direction to avoid damaging the valuable timber, while ensuring it didn't land on anyone who couldn't dodge several tons of falling wood with the agility of a professional dancer. Once felled, the logs had to be transported to the shipyard using methods that predated mechanical assistance by several centuries. This involved systems of ropes, pulleys, wooden rollers, and human muscle power applied in ways that tested both physics and prayer. Moving a single massive log could require dozens of people working in coordination for days, navigating terrain that seemed specifically designed to make the process impossible. The logs would arrive at the shipyard scarred, dirty, and requiring months of careful preparation before they could be transformed into ship components. Each piece had to be examined for flaws, measured for suitability, and seasoned to remove moisture that could cause warping, splitting, or rot once the ship was completed. Seasoning timber was a process that required patience measured in years rather than weeks. Greenwood, freshly cut timber, contained moisture that made it unstable and prone to dimensional changes as it dried. Properly seasoned wood had been dried slowly and evenly, reducing moisture content to levels that wouldn't cause problems later, but maintaining enough flexibility to be worked without cracking. But ancient shipbuilders didn't always have years to season their timber properly, especially when merchants were demanding completion dates that ignored the realities of material preparation. This meant working with wood that was less than ideal, compensating for potential problems through construction techniques that assumed the materials would behave unpredictably, and hoping that experience could overcome the limitations of inadequate preparation time. Your first major lesson in shipbuilding physics came when you learned about the keel, the ship's backbone, the structural foundation that everything else would be attached to. The keel had to be absolutely straight, incredibly strong, and precisely positioned, because every other component of the ship would be measured and fitted relative to this single piece. Laying the keel was a ceremony that combined practical construction with ritual significance. The master shipwright would supervise every aspect of the process, from the initial placement to the final securing, because mistakes at this stage would affect every subsequent phase of construction. The keel had to be level, properly supported, and positioned to allow access for workers who would be crawling around, under, and through the growing structure for months. Once the keel was established, you could begin attaching the ribs, the curved timbers that would define the ship's shape and provide structural support for the hull planking. Each rib had to be individually shaped to match the designer's vision of how the vessel should look and perform in water. This required understanding geometry that wasn't taught in schools, spatial reasoning that came from experience rather than textbooks, and physical skills that combined carpentry with sculpture. Shaping ribs involved heating timber to make it pliable, bending it to the required curve using forms and clamps, and securing it in position while the wood cooled and hopefully retained the desired shape. This process required perfect timing, too little heat, and the wood wouldn't bend. Too much heat, and it would char or crack. Too little pressure, and the curve wouldn't hold. Too much pressure, and the timber would split. The heating was done using steam generated in pits filled with seaweed, damp wood, and controlled fire that produced moisture. Laden heat rather than dry flames that would damage the timber. You'd work in conditions that combined a sauna with a construction site, wearing minimal clothing, because fabric would stick to your skin in the humid environment, while handling tools that were hot enough to cause serious burns. Working with steam timber required gloves made from thick leather that provided protection while allowing enough dexterity to manipulate tools with precision. The leather would become saturated with moisture, making it slippery and unreliable just when you needed maximum grip strength to control pieces of wood that wanted to spring back to their original shapes with enough force to break bones. Each rib had to be fitted to the keel with joints that would remain strong under the stresses of oceanic conditions. These joints were cut by hand using chisels and saws that required constant sharpening and careful handling. A poorly cut joint would weaken the entire structure, while a perfectly cut joint would distribute stress evenly and contribute to the ship's overall strength and longevity. The joinery techniques used in ancient shipbuilding were sophisticated engineering solutions developed through generations of trial, error, and catastrophic failure. Mortise and tenon joints locked pieces together mechanically. Scarfing joints allowed shorter pieces of timber to be combined into longer structural elements. Dovetail joints prevented components from pulling apart under tension. But creating these joints with hand tools required skills that took years to develop and physical strength that challenged even the most robust apprentices. Cutting a mortise, a rectangular hole designed to receive a tenon, involved removing precise amounts of wood using chisels that had to be driven by mallets with exactly the right amount of force. Too little force, and you'd be chipping away for hours. Too much force, and you'd split the timber or drive the chisel through your hand. The tenon, the protruding piece that fit into the mortise, had to be shaped to exact dimensions, using tools that removed wood in thin shavings rather than large chunks. This required understanding how different types of wood responded to cutting tools, how grain direction affected the ease of removal, and how environmental conditions like humidity and temperature influenced the wood's behavior. Testing the fit of joints was an iterative process that involved careful measurement, patient adjustment, and the kind of attention to detail that would drive modern workers to nervous breakdowns. Each joint had to fit perfectly, tight enough to remain secure under stress, loose enough to allow for the slight dimensional changes that occurred as wood continued to season after installation. Once the basic framework was complete, you could begin planking, attaching the wooden skin that would actually keep the water outside where it belonged. Planking was where shipbuilding transformed from carpentry into something approaching black magic, because you were creating a watertight barrier using materials that naturally contained gaps, joints, and imperfections. Each plank had to be individually shaped to follow the compound curves of the ship's hull. This wasn't like installing straight boards on a flat wall. Each piece required unique curves in multiple dimensions, edges that matched perfectly with adjacent planks, and fastening systems that would remain secure under conditions that would test every joint and connection. Shaping planks involved techniques that combined traditional woodworking with maritime, specific skills that weren't used in any other construction application. The planks had to be bent not just in one direction, but in complex curves that matched the three-dimensional shape of the hull. This required understanding how wood fibers behaved under stress, how different species responded to bending forces, and how to achieve the required curves without creating weak points that would fail under load. The bending process involved controlled application of heat and moisture, combined with mechanical force applied gradually over time. Rushing the process would result in cracked or split planks that were worthless for their intended purpose. Taking too long would allow the wood to cool and stiffen before the desired shape was achieved. The timing had to be perfect, and perfection came from experience that was earned through years of ruined planks and frustrated masters. Fastening the planks to the ship's framework required techniques that would hold under conditions ranging from calm seas to violent storms. The primary fastening method involved wooden pegs called tree nails, essentially hardwood dowels that were driven through drilled holes to lock planks to the underlying ribs. Creating tree nails was a specialized skill that required understanding how different woods expanded and contracted under varying moisture conditions. The tree nails had to be made from wood that would swell when wet, creating a tight mechanical connection that would actually improve as the ship was exposed to seawater. Oak tree nails were preferred because they would expand when exposed to moisture, creating joints that became tighter and stronger over time. Drilling the holes for tree nails required precision that would challenge modern power tools. The holes had to be perfectly aligned between the plank and the underlying rib, sized to create the proper interference fit with the tree nail, and positioned to avoid weakening either component. This was accomplished using hand-powered augers that required significant strength to operate and careful technique to maintain accuracy. The auger, essentially a large drill bit with a wooden handle, had to be turned while applying downward pressure sufficient to cut through hardwood timber. The cutting had to be done slowly enough to maintain accuracy, but quickly enough to prevent the bit from binding in the wood. If the auger became stuck, removing it without damaging the partially drilled hole required patience and techniques that weren't taught in any manual. Once the holes were drilled, the tree nails had to be driven home using wooden mollets that provided sufficient force without damaging the peg or the surrounding wood. Each tree nail had to be inserted exactly perpendicular to the surface, driven to the proper depth, and secured in a way that would prevent it from working loose under the constant stress of shipboard conditions. But tree nails were just one aspect of the fastening system. Critical joints also required iron bolts, which presented their own set of challenges in an era when metallurgy was more art than science. Iron bolts had to be forged to exact specifications, shaped to fit specific applications, and installed using techniques that prevented corrosion while ensuring mechanical integrity. Working with iron bolts meant coordinating with blacksmiths who understood marine applications and could produce fasteners that would perform reliably in saltwater environments. This required communication between craftsmen who spoke different technical languages, shared responsibility for components that had to work together perfectly, and mutual understanding of failure modes that could sink ships and kill crews. The bolts had to be installed using techniques that sealed the holes against water intrusion while maintaining the mechanical strength of the connection. This involved washers, gaskets, and sealing compounds that were applied with methods passed down through generations of shipbuilders who'd learned through experience what worked and what led to disaster. Once the basic hull was planked and fastened, the real challenge began making it watertight through a process called caulking that was equal parts craftsmanship and voodoo. Caulking involved stuffing the gaps between planks with materials that would swell when wet, creating a flexible seal that could accommodate the dimensional changes that occurred as the ship flexed in seaway conditions. The primary caulking material was oakum, old rope, that had been picked apart into individual fibers and mixed with tar or pitch to create a waterproof compound. Preparing oakum was tedious work that was typically assigned to apprentices who demonstrated they could be trusted with materials that were expensive and time-consuming to prepare. Picking oakum involved taking old, worn rope and carefully separating it into component fibers without creating waste. The rope had to be selected for appropriate fiber content, condition, and length. Rope that was too deteriorated would produce weak caulking that would fail under stress. Rope that was too new was wasteful of materials that could be better used for running rigging or other applications. The separated fibers were mixed with tar or pitch that had been heated to the proper consistency, hot enough to penetrate the fibers completely, cool enough to handle without causing serious burns. The mixing had to be done quickly because the tar would harden as it cooled, creating lumps that were difficult to work with and ineffective as waterproof sealant. Installing the oakum required tools specifically designed for forcing fibrous material into narrow gaps with enough pressure to create effective seals. The caulking iron, a chisel-like tool with a blunt edge, was used to drive oakum into the seams between planks. The work required precise control of force applied through tools that could easily damage the planking if used incorrectly. Each seam had to be caulked to exactly the right density, too little oakum, and the seam would leak. Too much oakum and the excessive pressure could split the planks or create stress concentrations that would cause problems later. The proper density was determined by experience, feel, and understanding of how different wood species responded to the installation process. The caulking had to remain flexible enough to accommodate the movement that occurred as the ship worked in seaway conditions, while providing a seal effective enough to keep the ocean outside where it belonged. This required understanding the dynamic loading conditions that ships experienced, the materials science of wood and tar combinations, and the long-term performance characteristics of caulking systems under marine exposure. But caulking was just the beginning of the waterproofing process. The exterior of the hull had to be treated with additional protective coatings that would resist marine organisms, prevent rot, and maintain watertight integrity over the ship's operational lifetime. This involved applications of tar, pitch, and other compounds that were applied in multiple coats using techniques that ensured complete coverage and proper adhesion. The protective coatings had to be applied in specific environmental conditions, not too hot, not too cold, not too humid, not during precipitation. The timing had to coordinate with tides, weather patterns, and the availability of materials that might have to be imported from distant locations. Everything had to come together perfectly, or the entire process would have to be repeated at considerable expense in time and materials. Meanwhile, while the hull was being made watertight, other craftsmen were working on the internal structure that would support cargo, crew, and the ship's operational equipment. This involved creating decks, bulkheads, and compartments that subdivided the interior space into functional areas while maintaining the structural integrity of the overall vessel. Deck construction required understanding how to create flat surfaces that would remain stable under conditions that included not only the normal stresses of cargo loading, but also the dynamic forces created by storms, heavy seas, and combat operations if the ship was intended for military use. The decks had to be strong enough to support concentrated loads while flexible enough to work with the hull as the ship flexed in seaway conditions. The deck planking had to be fitted with the same precision required for hull planking, but with additional considerations for drainage, access to below deck spaces, and the mounting of equipment that would be secured to the deck structure. Each plank had to be shaped to follow the curve of the deck, fitted tightly against adjacent planks, and fastened to the underlying deck beams using techniques that would remain secure under the worst imaginable conditions. Deck caulking required the same materials and techniques used for hull caulking, but with additional challenges created by the fact that deck seams were horizontal rather than vertical. Water would tend to pool in deck seams, creating persistent moisture conditions that could cause premature failure of caulking materials. The seams had to be shaped and sealed in ways that encourage water to drain rather than accumulate. Creating hatches, the openings that provided access to below deck spaces, required precision fitting that would maintain watertight integrity, while allowing the openings to be sealed during severe weather conditions. Each hatch had to be fitted with covers that could be secured quickly and effectively, gaskets that would prevent water intrusion, and fastening systems that would remain operable under emergency conditions. The hatches also had to be sized and positioned to allow cargo handling operations, crew movement, and emergency access while minimizing the weakening effect of large openings in the deck structure. This required understanding the structural engineering of the overall vessel and how modifications affected the distribution of stress throughout the ship's framework. Bulkheads, the internal walls that subdivided the ship's interior, served multiple functions that went beyond simple space division. They provided structural support that prevented the hull from deforming under load, created compartments that could limit flooding if the hull was damaged, and organized the interior space in ways that facilitated cargo handling and crew operations. Each bulkhead had to be fitted to the irregular interior shape of the hull, fastened to both the hull structure and deck beams, and sealed to prevent the passage of water between compartments. This required understanding how the ship's structure would change shape under different loading conditions and designing connections that would accommodate movement without compromising watertight integrity. The fastening systems for bulkheads involved combinations of mechanical connections and adhesive sealants that would maintain their effectiveness under the constant vibration and stress cycling that characterized shipboard conditions. The connections had to be accessible for maintenance and repair while remaining secure under normal and emergency operating conditions. But while all this internal work was progressing, other specialists were creating the rigging and sail handling systems that would actually make the ship capable of controlled movement under wind power. This involved understanding aerodynamics principles that wouldn't be formally codified for centuries, materials science of rope and canvas, and mechanical engineering of pulleys, blocks, and other hardware. The mast, the vertical spar that supported the sails, had to be created from timber that met specifications more demanding than any other single component of the ship. The mast timber had to be straight-grained, not free, and sized to provide adequate strength, while remaining light enough not to compromise the ship's stability characteristics. Finding suitable mast timber often required searching forests across vast distances, negotiating with landowners who understood the premium value of perfect mast trees, and arranging transportation that could move massive logs without damage from the forest to the shipyard. A single mast timber might represent months of searching and weeks of transportation effort. Shaping the mast required removing material while maintaining precise dimensional control and avoiding any modifications that would create stress concentrations or weak points. The mast had to taper according to engineering requirements that balanced strength, weight, and aerodynamic considerations. Too much taper and the mast would be weak at the top, too little taper and it would be unnecessarily heavy and affect the ship's stability. The mast also had to be fitted with hardware that would support the rigging loads transmitted from the sails during normal and storm conditions. This involved creating mortises for mast steps, holes for shroud attachments, and mounting points for yards and other rigging components. Each modification had to be precisely located and carefully executed to avoid weakening the mast structure. Installing the mast required coordination between multiple crews using lifting equipment that was essentially medieval technology applied to loads that challenged the capabilities of the available machinery. The mast had to be raised vertically and positioned precisely over the mast step, then lowered carefully until it seated properly in the ship's structure. The rigging, the network of ropes, and hardware that controlled the sails represented a complex engineering system that had to function reliably under conditions ranging from calm weather to life-threatening storms. Each rope had to be sized for the loads it would carry, positioned to avoid interference with other components, and secured using knots and hardware that would remain functional after months of exposure to salt water and weather. Creating the rigging required understanding the forces generated by sails under different wind conditions, the mechanical advantage provided by different pulley configurations, and the materials science of rope construction and performance. The rigging also had to be arranged in ways that allowed sailors to operate the ship safely and efficiently while providing backup systems that could function if primary components failed. The ropes themselves had to be manufactured from materials that would retain strength and flexibility under marine conditions. This typically involved hemp or flax fibers that were twisted into strands, then combined into ropes using techniques that distributed load evenly and prevented premature failure due to localized stress concentrations. Rope making was a specialized craft that required understanding fiber preparation, twist rates, tension control, and quality assessment techniques that ensured the finished product would meet marine performance requirements. Poor quality rope could cause sail handling failures that would endanger the ship and crew, while high-quality rope would perform reliably for years under demanding conditions. The sails themselves represented the most complex textile engineering challenge of the ancient world. Each sail had to be shaped to provide efficient aerodynamic performance while remaining strong enough to survive the forces generated by storm, force winds. The sail cloth had to be woven from fibers that could maintain strength and flexibility under constant UV exposure, salt spray, and mechanical stress. Creating sailcloth involved weaving techniques that produced fabric with the strength characteristics required for marine use, while maintaining the flexibility needed for proper aerodynamic shape. The weaving had to be tight enough to prevent excessive air leakage, while remaining loose enough to allow folding and handling operations. The individual pieces of sailcloth had to be joined using stitching techniques that would distribute loads evenly and prevent progressive failure if individual seams were damaged. This required understanding how different stitching patterns performed under various loading conditions and selecting techniques appropriate for each application. Shaping the sails required understanding three-dimensional geometry that allowed flat pieces of cloth to be assembled into curved surfaces that would maintain proper aerodynamic shape under wind loading. This involved calculations and layout techniques that predated formal engineering analysis by centuries, but achieved results that modern computer modeling confirms were remarkably sophisticated. But even after the ship was structurally complete, rigged, and ready for launch, the real test was still ahead, getting it into the water without destroying months of work in a few catastrophic minutes. Launching a ship was an engineering challenge that required moving a massive, irregularly shaped object from land to water using techniques that were basically sophisticated applications of leverage, friction control, and prayer. The ship had to be supported on ways, inclined ramps, that would allow it to slide into the water under controlled conditions. Building the ways required understanding soil mechanics, structural engineering, and the dynamics of objects moving down inclined planes under the influence of gravity and friction. The ways had to be strong enough to support the ship's weight, while slippery enough to allow controlled movement. They also had to be positioned to ensure the ship would enter the water at the proper angle and speed. The ways were typically constructed from heavy timbers that were shaped to match the ship's hull and coated with tallow, soap, or other lubricants that would reduce friction to manageable levels. The lubrication had to be applied evenly and refresh it as needed to prevent binding or uncontrolled acceleration during the launch process. Controlling the launch required systems of ropes, anchors, and braking devices that could regulate the ship's movement down the ways and prevent it from entering the water too quickly or at the wrong angle. These control systems had to be operated by crews who understood the timing and coordination required for safe launch operations. The actual launch was typically scheduled to coincide with high tide, which provided maximum water depth at the bottom of the ways and reduced the distance the ship would have to slide before becoming waterborne. The timing had to account for tidal cycles, weather conditions, and the readiness of all personnel and equipment involved in the operation. If the launch went well, the ship would slide gracefully into the water and float upright, ready for final fitting out and sea trials. If the launch went poorly, months of work could be destroyed in minutes through damage caused by uncontrolled movement, improper entry angle, or structural failure under launch stresses. But even a successful launch was just the beginning of the testing process that would determine whether the ship was actually seaworthy or just an expensive floating disaster waiting to happen. Sea trials involved systematic testing of all ship systems under progressively more demanding conditions, from calm, weather maneuvering to storm, force weather operation. The initial trials tested basic buoyancy, stability, and handling characteristics under ideal conditions. The ship was loaded with ballast to approximate normal operating weight distribution, then taken to sea with minimal crew and cargo to evaluate how it performed under controlled conditions. Basic stability testing involved deliberately heeling the ship to various angles and observing how it responded to the imposed forces. A properly designed ship would return to upright position when the heeling force was removed, while an improperly designed ship might remain heeled, or in the worst case, continue rolling until it capsized. Handling tests evaluated how the ship responded to rudder inputs, how effectively it could be maneuvered in confined spaces, and how well it maintained course under different wind and sea conditions. These tests revealed design problems that might not be apparent from static analysis, but could cause serious operational difficulties under real-world conditions. Loading tests determined how the ship's performance characteristics changed as cargo was added, and how weight distribution affected stability, handling, and seakeeping ability. Improper loading could transform a seaworthy vessel into a dangerous liability that would endanger crew and cargo under conditions that should have been manageable. If the initial trials revealed serious problems, the ship might have to be returned to the shipyard for modifications that could range from minor adjustments to major structural changes. In extreme cases, ships that failed sea trials were declared unseaworthy, and either converted to other uses or broken up for materials recovery. But if the trials went well, the ship would be accepted by its owners and begin its working life carrying cargo, passengers, or military equipment across waters that would test every aspect of its design and construction for years or decades to come. Your role in this process was simultaneously crucial and invisible. The skills you developed over years of apprenticeship and practice were embedded in every joint, every plank, and every component of the finished vessel. Your craftsmanship would be tested by conditions you'd never experience personally, in places you'd never visit, under circumstances you could only imagine. The ship would sail to distant ports, survive storms that would terrify experienced sailors, and carry loads that would stress every component you'd helped create. If your work was good, the ship would perform its intended function for years while generating profits that would support families, communities, and entire economies. If your work was flawed, the consequences might not become apparent until the ship encountered conditions that revealed weaknesses in design or construction. A poorly cut joint might fail during a storm, causing structural damage that could sink the vessel. Inadequate caulking might allow progressive flooding that would overwhelm the crew's ability to manage water ingress. But success or failure often wouldn't be known for months or years after completion. When the ship was operating in distant waters under conditions that bore no resemblance to the controlled environment of the shipyard, you'd move on to the next project, applying lessons learned from previous work while wondering how your previous creations were performing in their intended service. The cycle would repeat with each new commission: timber selection, shaping, fitting, fastening, caulking, rigging installation, and all the countless details that transformed dead trees into living vessels capable of carrying civilization across the oceans that separated continents and cultures. Each ship represented thousands of individual decisions, compromises between competing requirements, and solutions to problems that had no perfect answers. Materials that were strong enough might be too heavy, while materials that were light enough might not be strong enough. Construction techniques that were fast might not be durable, while techniques that were durable might be too slow for competitive completion schedules. Your expertise developed through experience with these trade-offs, understanding gained through years of seeing how different approaches performed under real-world conditions, and intuition that came from handling materials and tools until their behavior became predictable and manageable. But the ancient shipbuilding industry was more than just individual craftsmanship. It was a complex economic and social system that connected forest resources with maritime commerce, skilled labor with capital investment, and local construction capabilities with international trade networks. The shipyards themselves were major employers that supported entire communities through direct wages and indirect economic activity. A large shipyard might employ hundreds of workers with specialized skills, creating demand for housing, food, tools, and other goods and services that supported the broader local economy. The economic relationships were complex and interdependent. Shipowners provided capital and assumed financial risk, while shipbuilders provided labor and expertise. Timber suppliers, metalworkers, rope makers, and other specialists contributed materials and components that had to meet marine performance standards while remaining cost competitive with alternative sources. The international nature of maritime commerce meant that ships built in one location might spend their entire operational lives in distant waters, carrying cargo between ports that had different languages, currencies, legal systems, and cultural expectations. This created requirements for standardization that crossed national boundaries and technical specifications that had to be understood by craftsmen who shared no common language except the universal demands of seaworthiness. But it also created opportunities for innovation and knowledge transfer that accelerated the development of shipbuilding technology. Techniques that proved successful in one region could be adapted and improved by craftsmen in other areas, while design failures could be analyzed and avoided through communication networks that connected shipyards across vast distances. Your individual contribution to this system was simultaneously small and essential. You were one of thousands of craftsmen working in shipyards around the ancient world, applying similar skills to similar problems using techniques that had been developed and refined over generations of practical experience. But your individual craftsmanship was also unique and irreplaceable. The specific combination of skills, experience, and attention to detail that you brought to each project could mean the difference between a ship that performed reliably for decades and one that failed catastrophically during its first major storm. The responsibility was both inspiring and terrifying. Every morning, you'd wake up knowing that somewhere in the world, ships you'd helped build were carrying people whose lives depended on your ability to cut a joint properly, install a fastener correctly, or seal a seam effectively. It was enough to drive a reasonable person to drink, which explains why shipyard taverns were legendary for their quality and their clientele's capacity for alcohol. But let's talk about the seasonal realities of ancient shipbuilding, because this wasn't a profession that operated on convenient modern schedules. Your work life was dictated by weather patterns, resource availability, and the agricultural cycles that determined when labor was available for non-farming activities. Winter was simultaneously the best and worst time for shipbuilding. Best because it was when most agricultural workers were available for other employment, providing the labor force needed for major construction projects. Worst because it was when working conditions became a daily exercise in surviving exposure, while trying to perform precision craftsmanship with hands that had lost feeling hours ago. The shipyard in winter was a special kind of purgatory designed by people who believed that comfort was incompatible with quality work. The tools were cold enough to remove skin if you touched them without proper protection. The wood was cold enough to shatter if worked improperly. The adhesives and sealants became so thick they had to be heated before use, creating opportunities for burns that would incapacitate you for weeks. But winter was also when the most complex and demanding work was typically scheduled, because the long nights provided uninterrupted time for tasks that required extended periods of concentration. Shaping critical structural components, fitting complex joints, and creating the precise curves required for hull planking were all winter activities that took place by firelight in conditions that would violate every modern workplace safety regulation. The fires used for heating tools and workspaces created additional hazards in environments filled with wood shavings, tar, and other flammable materials. Fire prevention required constant vigilance from workers who were already managing multiple safety hazards while trying to maintain productivity levels that would satisfy demanding schedules and quality requirements. Spring brought different challenges as the shipyard emerged from winter's constraints and began preparing for the intensive construction season ahead. This was when major timber deliveries arrived, when new apprentices were hired and trained, and when projects that had been planned during winter's enforced indoor period finally began taking physical form. The spring timber deliveries were events that transformed the entire shipyard as massive logs arrived from forests that might be hundreds of miles away. Each delivery had to be evaluated for quality, sorted by intended use, and positioned for seasoning and preparation. This required coordination between multiple crews, heavy lifting equipment that tested the limits of available technology, and storage systems that protected valuable materials from weather and theft. The logs arrived with their own problems: checking and splitting that had occurred during transport, insect damage that might not be immediately visible, and dimensional changes that occurred as the wood adjusted to new environmental conditions. Each piece had to be inspected, measured, and evaluated for suitability before it could be incorporated into construction plans. Preparing the newly arrived timber for use required techniques that balanced the need for rapid processing against the risks of damaging valuable materials through hasty work. Each log had to be evaluated for hidden defects, marked for optimal cutting patterns, and processed using methods that maximized the yield of usable lumber while minimizing waste. The sawing was done using hand tools that required teams of workers operating in careful coordination. The pit saw, essentially a large saw blade operated by two people, one above and one below the log, could produce planks of specified thickness, but only through hours of backbreaking labor that demanded precise technique and sustained physical effort. The worker in the pit, usually the junior member of the team, worked in conditions that combined the worst aspects of manual labor with claustrophobic confinement. Sawdust rained down constantly, the workspace was cramped and poorly ventilated, and the physical demands of the sawing motion had to be sustained for hours at a time. The worker above the log had to guide the saw blade along marked lines while maintaining the rhythm and pressure needed for efficient cutting. This required understanding how different types of wood responded to sawing, how blade maintenance affected cutting performance, and how environmental conditions influenced the behavior of both the wood and the cutting tools. But even perfectly sawn lumber was just raw material that required months of additional preparation before it could be incorporated into ship construction. The planks had to be stacked for air drying using techniques that promoted even moisture loss, while preventing warping, checking, and other defects that would make the lumber unsuitable for marine use. Stacking lumber for drying required understanding airflow patterns, moisture management, and the behavior of different wood species under drying conditions. The stacks had to be positioned to take advantage of prevailing winds, while being protected from precipitation that could re-wet the lumber and promote rot or insect infestation. The stacking itself required careful attention to weight distribution, support spacing, and the use of stickers, thin strips of wood that separated the layers and allowed air circulation around each piece. Improper stacking could result in warped lumber, uneven drying, or collapse of the entire stack with potential for serious injury to anyone working nearby. Summer was the peak construction season when weather conditions allowed the most demanding outdoor work and when completion schedules required maximum productivity from all available labor. This was when hulls were planked, when major assembly operations took place, and when the race against time and weather determined whether projects would be completed successfully or become expensive failures. The summer heat created different challenges from winter cold, but challenges that were equally demanding and potentially more dangerous. Working with tar and pitch in hot weather required protective equipment that was often inadequate for the conditions, while the physical demands of heavy construction work in high temperatures pushed human endurance to its limits. The hot tar used for waterproofing became more fluid and easier to apply in warm weather, but also more dangerous to handle and more likely to cause severe burns if accidentally contacted. The vapors from heated pitch could cause respiratory problems, while prolonged exposure to tar-based compounds could cause skin irritation and other health issues that wouldn't be understood for centuries. But summer was also when the most satisfying aspects of shipbuilding became apparent as months of individual component preparation finally came together in the form of recognizable vessels that looked increasingly like the ships they were intended to become. The hull would take shape as planking covered the skeletal framework. Decks would be installed to create functional interior spaces, and rigging would begin to transform the structure into something capable of controlled movement. The assembly process required coordination between multiple specialized crews working on different aspects of the same vessel. The timing had to be precise to avoid conflicts between different operations, while ensuring that each phase of construction was completed in the proper sequence and to the required quality standards. Communication between crews was essential but challenging because the different specialties involved their own technical vocabularies, quality standards, and traditional methods that might not be immediately compatible with the approaches used by other craftsmen. Achieving the necessary coordination required experience, patience, and leadership skills that went beyond technical expertise. But summer also brought the pressure of completion deadlines that were often driven by commercial considerations rather than realistic assessments of the time required for quality construction. Merchants wanted their ships completed in time for favorable sailing seasons, while shipyard owners needed to maintain cash flow through timely delivery of finished vessels. These schedule pressures could lead to shortcuts that compromised quality, rushed work that introduced defects, and decisions that prioritized immediate delivery over long-term performance. Managing these pressures required balancing commercial realities against professional standards while maintaining the reputation for quality that was essential for future business. Autumn brought the culmination of the construction season as completed vessels were prepared for launch and delivery to their owners. This was when the year's work was finally tested through the complex and dangerous process of moving massive structures from land to water, using techniques that had changed little over centuries. The pre-launch preparation involved final inspections that checked every aspect of the vessel's construction, from structural integrity to waterproof sealing to the proper installation and operation of all onboard systems. These inspections were conducted by experienced masters who understood the critical factors that determined seaworthiness and could identify potential problems before they became catastrophic failures. The inspection process was systematic and thorough, covering structural components, fastening systems, waterproofing installations, rigging arrangements, and all the countless details that had to function properly for safe operation. Each deficiency had to be corrected before launch, often under time pressure that made proper repairs challenging and expensive. But the inspections also served as final quality control that protected both the shipyard's reputation and the safety of future crews and passengers. A ship that failed its pre-launch inspection might require weeks of additional work, but a ship that was launched with undetected defects could cause losses of life and property that would destroy the shipyard's business and the careers of everyone involved. The launch itself remained one of the most dramatic and dangerous aspects of the entire construction process. Despite centuries of experience and refined techniques, moving a massive vessel from land to water involved forces and dynamics that couldn't be completely controlled or predicted. The launch preparations required days of careful work to ensure that all systems were properly positioned and tested. The ways had to be inspected and prepared, the control lines had to be rigged and tested, and all personnel had to be briefed on their responsibilities and the emergency procedures that might be needed if something went wrong. The timing of the launch was critical and had to account for multiple factors that might not be controllable. Tidal conditions determined the water depth available at the bottom of the ways. Weather conditions affected both the safety of the operation and the behavior of the ship once it became waterborne. The availability of personnel and equipment determined whether the launch could proceed as scheduled or would have to be postponed. But when everything came together properly, the launch was a moment of triumph that justified months of demanding work and demonstrated the transformation of raw materials into functional vessels capable of carrying civilization across the world's oceans. The ship would slide down the ways with increasing speed, generating momentum that carried it into the water with enough velocity to achieve proper flotation before friction could cause it to stop short of deep water. The entry had to be controlled to prevent damage from excessive speed, while ensuring adequate penetration into water deep enough to support the vessel's full weight. Once waterborne, the ship had to demonstrate immediate stability and buoyancy that confirmed the accuracy of the design calculations and construction techniques. A properly launched vessel would float upright at its designed waterline, respond normally to wind and wave forces, and show no signs of leakage or structural distress. But launch was just the beginning of the acceptance process that would determine whether the completed vessel met the specifications agreed upon between the shipyard and the customer. The sea trials that followed would test every aspect of the ship's design and construction under conditions that simulated its intended operational environment. These trials were conducted with minimal crew and cargo to reduce the risks associated with testing unproven vessels under demanding conditions. The initial tests focused on basic handling characteristics, stability behavior, and structural integrity under normal sailing conditions. As confidence in the vessel's performance increased, the trials became progressively more demanding, testing the ship's ability to handle heavy weather, maximum loading conditions, and emergency situations that might be encountered during normal operations. Only after successful completion of all trials would the ship be accepted by its owners and released for commercial service. Your involvement in this process was both complete and limited. Complete because your craftsmanship was embedded in every aspect of the vessel's construction and would determine its performance throughout its operating life. Limited because once the ship was launched, your direct responsibility ended and its fate would be determined by factors beyond your control. But the knowledge that ships you'd helped build were operating successfully in distant waters carrying valuable cargoes and precious human lives, provided satisfaction that justified the demanding apprenticeship, dangerous working conditions, and personal sacrifices that characterized the ancient shipbuilding profession. Each successful vessel validated the techniques you'd learned, the skills you'd developed, and the standards you'd maintained throughout years of challenging and often thankless work. Each ship that returned safely to port after surviving storms, navigational hazards, and the countless dangers of ancient maritime commerce represented a personal victory that few people outside the profession could fully understand or appreciate. But the profession also extracted its toll through injuries that were considered normal occupational hazards, health problems that were accepted as inevitable consequences of the work, and family sacrifices that were required by the demanding schedules and seasonal nature of the construction cycles. The injury rate in ancient shipyards would horrify modern safety professionals, but was accepted as the unavoidable cost of working with dangerous materials using primitive tools under demanding conditions. Cuts from sharp tools, burns from hot pitch, crushing injuries from heavy timbers, and falls from heights were common experiences that most shipbuilders survived, but which left permanent reminders of their profession's hazards. The chronic health effects were less obvious, but equally inevitable. Joint problems from years of heavy lifting and awkward working positions, respiratory issues from inhaling wood dust and chemical vapors, and skin conditions from constant exposure to tar and other harsh substances were the price paid for decades of professional expertise. But despite these costs, the profession attracted men who found satisfaction in creating vessels that would outlast their builders and carry the achievements of human civilization to distant shores. The combination of technical challenge, creative expression, and practical utility that characterized shipbuilding provided rewards that compensated for the physical demands and personal sacrifices. The social status of skilled shipbuilders reflected the essential nature of their work in economies that depended on maritime commerce for survival and prosperity. Master shipwrights were respected craftsmen whose expertise was valued by merchants, nobles, and governments that understood the strategic importance of superior naval technology. But this respect was earned through demonstrated competence rather than inherited position, and had to be maintained through continued success in an unforgiving profession where failures were measured in lives lost and fortunes destroyed. The pressure to maintain professional reputation while meeting increasingly demanding commercial and technical requirements was a constant source of stress that accompanied the satisfaction of creative achievement. The legacy of ancient shipbuilding extended far beyond the individual vessels that were constructed during any single generation. The techniques developed through centuries of trial and error, the materials science knowledge gained through practical experience, and the organizational methods required for complex construction projects provided foundations for technological advancement that would continue for millennia. Each generation of shipbuilders inherited the accumulated wisdom of their predecessors while adding their own innovations and improvements to the body of professional knowledge. The continuous evolution of techniques, materials, and design concepts created a technological tradition that connected the earliest maritime civilizations with the modern world. Your individual contribution to this tradition was simultaneously modest and essential. Modest because you were one of thousands of craftsmen working within established traditions using techniques that had been developed by previous generations. Essential because the tradition could only continue through the dedicated efforts of individuals who maintained standards, preserved knowledge, and passed skills to the next generation of apprentices. The ancient shipbuilding profession represented humanity's most sophisticated pre-industrial technology, combining advanced understanding of materials science, structural engineering, and fluid dynamics with organizational capabilities that could coordinate complex projects involving hundreds of skilled workers over periods of months or years. But it also represented the human capacity for accepting extraordinary personal risk and sacrifice in pursuit of goals that extended beyond immediate self-interest. The men who built the ships that carried ancient civilizations across the world's oceans understood that their individual efforts were part of something larger and more enduring than their own lives. This understanding provided meaning that compensated for the hardships, dangers, and personal costs of the profession. The knowledge that ships you'd helped build would carry explorers to unknown lands, merchants to profitable markets, and colonists to new homes provided a sense of purpose that few other occupations could match. And so the ancient shipbuilding tradition continued, generation after generation, each group of craftsmen building upon the achievements of their predecessors, while facing the eternal challenges of transforming dead trees into living vessels capable of carrying human dreams across the vast and dangerous expanses of the world's oceans. The tradition would evolve and adapt to changing technologies, materials, and requirements, but the fundamental challenges would remain constant: the need for technical excellence, the demand for absolute reliability, and the responsibility for creating vessels that would protect precious human lives in environments that showed no mercy for inferior craftsmanship. Your place in this tradition was both humble and heroic, defined not by individual achievement, but by faithful participation in humanity's ongoing effort to master the seas that both separated and connected the world's civilizations. The ships you helped build became part of history, carrying not just cargo and passengers, but the hopes and ambitions of entire cultures seeking their destinies beyond the horizon. This was the life of an ancient shipbuilder, demanding, dangerous, and ultimately rewarding in ways that connected individual craftsmanship with the grand sweep of human civilization's expansion across the waters that covered most of the world's surface. It was work that mattered, performed by people who understood that their skills and dedication were essential elements in humanity's greatest adventure, the conquest of the sea.